going to go ahead and start chapter 3. Chapter 3 is over molecules, compounds, and chemical equations. So the first thing we want to talk about is chemical bonds. Now, the way to hold atoms together is by using bonds. Okay, so chemical bonds is some way how the atoms can kind of stick together somehow. So how are they connected together? There's two ways here. One is ionic bond, where you have opposite charge ions. Cations and anions are attracted to each other, the opposite charges, and they'll form an ionic bond. So in this case here, you see how the negative is attracted to the positive. Same idea there, so opposite charges. So this is an electrostatic force bond where you have plus charges and negative charges, and then that's how you form ionic bonds. Now, in general, cations are made from metal and anions are made from non-metal, so ionic bonds exist between metal atoms and non-metal atoms. There are some exceptions when we talk about polyatomic cations later, but that's later in this chapter. Okay, but in general, ionic bonds is going to have a metal and a non-metal because it requires a cation and an anion. So anytime you see a cation and anion, that's an ionic bond right there. Now, covalent bond is when it becomes too much effort for atoms to change itself into ions because they have to move too many electrons around. So what they do is instead of becoming ions, they share their electrons in a pool together. And we'll be learning more about this in later chapters as well. So generally, covalent bonds are when you have only non-metal and non-metal bond. Okay, so remember, ionic is plus minus charge. You have a metal and a metal cation and a non-metal anion. And covalent is when you just have non-metals bonding together by sharing electrons. All right, so let's talk about how we can represent compounds using formulas. So we have three types of formulas we want to focus on. Really, particularly these two we'll be talking a lot about. So we have empirical formula, molecular formula, and structural formula. We will be focusing a lot on empirical and molecular formula, okay? So chemical formulas are really useful. It tells us what's in the compound, what kind of atoms make the compound. So let's go over the first one. The first one is empirical formula. So what is empirical formula? It's basically a formula that tells you the simplest ratio of the atoms of each element inside the compound. So it's not necessarily exactly how many atoms, but it tells you the ratios of it. And they always give you the simplest number for the ratio. So for example, we have over here, empirical formula of a compound, oxalic acid, is CHO2. So CHO2 is the empirical formula. That means it tells you every time there's a C, there's going to be one H and there's going to be two O's. Okay, but that doesn't mean that's the actual formula. The actual molecular formula, which tells you all the correct actual numbers of atoms in there, is actually C2H2O4. So this is the real numbers of atoms in there, and empirical is just a simplified version, the simplest ratio there is, okay? So empirical formula for ionic compound, CaCl2 here, that means every time there's a calcium ion, there's gonna be two chloride ion paired with it. So empirical formula is the simplest ratio. Molecular formula tells you the actual number of atoms, okay? So in this case here, we just talked about oxalic acid. Oxalic acid was C2H2O4, okay? It just tells you there's gonna be two carbons in one molecule, two hydrogen in one molecule, and four oxygens in one molecule. But it doesn't exactly tell you how they're connected together. To see how they're connected together, you need a structural formula, okay? So let's take a look at structural formula. So a structural formula of oxalic acid looks like this, because it tells you exactly, okay, so not only do I know there was two carbon and four oxygen and two hydrogen, Now I know exactly how they're bonded. So this is the structural formula. A lot of times in lab, in class, you always will see the molecular formula and the empirical formula. Sometimes they write the molecular formula so you can kind of see how they're bonded, but it's nothing like a structural formula where it writes out exactly what's bonded to what, okay? And this is the model right here. We'll talk a little bit about models shortly. So on this structural formula here, single lines here are single bonds, double line here are triple bonds, double bonds, and six, if you see triple line, so these are double line here, so that's a double bond, that's a single bond, and if you see triple line here is a triple bond where you have 6 shared electrons. So each line represents 2 electrons, okay? So that's a single bond, 2 electrons. That's a double bond, 4 electrons. And if you ever see 3 lines together, that would be triple bond where you have 6 electrons. All right, so let's try some example here. It's kind of small. I'll read it out to you. It says here, write the empirical formula for these compounds. Let's zoom in a little bit. So the empirical formula for these molecular formulas, so molecular formulas tell you exactly how many atoms, remember? So this one, molecular formula C4H8, doesn't really tell you how it's bonded because it's not a structural formula, but that's enough to, for our question here. We only need to find the empirical formula. So if it's C4 and H8, what is the simplest ratio for 4 to 8? Well, it would be C1 and H2, agree? So the answer for empirical formula will be CH2. Okay, now let's take a look at B2H6. What's the simplest ratio for this one? It would be B1 and H3. You just divide it by 2 basically. So the answer for this guy would be BH3. Okay, now over here, what's the simplest formula for this guy? It's CCl4. So there's 1 carbon and 4 chlorine every time. Can you simplify this further? It can be simplified further. Agree? So sometimes the molecular formula is also the empirical formula, like C over here. So you will see they will tell you all these answers here. So CH2, BH3, and it says empirical formula and molecular formula here are identical. So we're looking at all those fancy little pictures of the ball and stick stuff. So these are molecular models. You won't have to draw them, so don't worry. But later in the semester, we will be using some models to look at geometry of our compounds here. So this will be kind of cool to be able to see in real life. So models show you a 3-dimensional view of what it's going to look like. So when you draw a picture like that, you can kind of see a little bit more in 3D dimension, okay? So let's take a look at a chart here. We have all these charts here now. The important thing is you can see, if I have a molecular formula C6H6, my empirical formula will be CH, and this is what the structure would look like. See how there's double bonds, there's single bonds, and are connected. Now this one here is where you have the triple bond, okay? There's a triple bond here where you have 6 electrons right there. So these are structural formulas that tell you exactly how they're bonded. Molecular formula tells you exactly how many atoms are. Empirical formula just tells you the simplest ratio. So then you see glucose here. Glucose is famous, so you can see what glucose looks like structurally, and this is the 3D model. The 3D model gives you a really pretty picture and sees exactly where the location of these atoms are. So C6H12O6 can be simplified to CH2O. So that's a molecular and that's empirical. Now in this case here, ammonia is so simple, the molecular formula is the same thing as the empirical formula. So that does happen. All right, so over here, now we want to be able to tell apart elements and compounds, okay? So we were talking about in chapter 1, before this, there was pure substance and there was mixtures. Under pure substance, there's elements and compounds, okay? And under mixtures, remember what's under mixture? It was heterogeneous mixture, which is the uneven mixture, and homogeneous mixture, which is the completely even mixture, okay? So under elements, elements means the stuff comes from only one box on your periodic table. Only one box. There's no other combination of boxes, just one thing from the periodic table. So under elements, it can be atomic element or molecular element. Atomic element means it's just one atom from the one element box right here. So in this case, they gave us neon as an example. That's right there. And neons come in atomic form because they're so stable, they don't have to bond, they don't do anything, they just stay as one atom. So that's what it looks like, neon. Now, molecular element means it's more than one atom, but from the same box. So in their example here, they gave you oxygen gas. See, oxygen gas is O2, but it comes from just this oxygen element, okay? So this here is molecular element, and it's actually diatomic because there's actually two atoms in there, right? So that's molecular element. So you need to be able to tell, okay, if you see Ne, that's atomic element, this one's molecular element, and then we want to look at compounds, okay? Compounds are where you have ionic compound or molecular compound. Ionic compounds comes from things with ionic bonds where you have a plus charge and a minus charge, okay? For example, Na is plus charge, Cl is negative charge. That's group 1 and group 7. Alkali, metal, and you have halogen, okay? So this is plus charge, minus charge, so that makes an ionic bond. So this is an ionic compound right here. Now, because that's metal and non-metal, and these are H and O, they're non-metal, and they will have molecular compounds being formed because these are from covalent bonds made by sharing the electrons, okay? So you'll want to be able to tell these apart. So let's go ahead and take a look at some example questions. Oh. So it says here, classify each of these substances as either an atomic element, molecular compound, or ionic compound. Okay, so let's take a look at this together. Xenon. What is xenon here? So xenon is Xe on our periodic table. Okay, so let me scoot the periodic table to show you. Right there, see? Number 54, okay? That's xenon. So xenon is a noble gas. It exists, noble gas are going to exist as single atoms. So what does this make it? It's an element and it's a single atom. So it would be an atomic element right there. Now, NiCl2. Ni is the transition metal nickel, okay? That's nickel right there. And then you want to look at Cl. That's metal. And Cl is under group 7 right here. Okay. That's a non-metal. That's negative charge. This one's positive charge. So what kind of compound? Well, it's a compound because it's more than one type of atom. But what kind of compound is this? This is an ionic compound because it makes an ionic bond. Bromine here, they should clarify. If they want to do bromine, they should write down this is Br2. Okay, bromine is group 7. Group 7, the stable form exists as diatomic. So everybody in group 7 here, these, they like to exist as diatomic form. That means it's F2, Cl2, Br2, I2, At2. Okay, they're in form of diatomic elements here. So because it's diatomic, what does it mean? It is a molecular element. Okay, because it's a molecule, there's 2 of them in there, so it makes it a molecule. So this one's atomic element, this one's molecular element, and that one's an ionic compound. So what about this guy? NO2. So that's not an element, it's a compound, okay? What kind of compound is it? Well, it's non-metal and non-metal because nitrogen and oxygen are both on the non-metal side. So let me show you that on the periodic table. Let me just zoom out a little bit. Well, right here, NNO, okay? Non-metal, group 5 and group 6, these are non-metal. So that means it is what kind of compound? It is a molecular compound, okay? What about this one? This one here is NaNO3. So nitrate is an ion right here. This is a negative ion, and sodium is a positive ion. That's positive cation, that's a metal. Sodium right here, okay, number 11. And then you have nitrate, NO3 negative ion. That's an anion, that's a polyatomic anion that we'll be seeing shortly. So this one here is gonna be an ionic bond, right? So between NaNO3, there's an ionic bond, so this is an ionic compound. Now, what's cool about NaNO3 is you actually have, to make this polyatomic ion right here, you actually have covalent bonds. So this thing here has covalent bonding and ionic bonding in the same compound. Isn't that cool? But anyway, that wasn't part of what the question asked. The question just wanted you to identify. So this is an ionic compound. And because it has a polyatomic ion in there, it also has covalent bond on top of the regular ionic bond. All right, so let's keep moving. Now we want to talk about writing ionic formulas when we talk about ionic compounds, okay? So after this, we'll learn how to name them. So when naming, you're gonna have to be memorizing some rules and how to name these things. So make sure you start making flashcards for this part of the chapter, okay? So when you wanna write ionic compounds, if it's the same charge, you just do a 1-to-1 ratio. If it's different charges, you know how they use the crisscross method? So you have Na plus and S2 negative, well, you just crisscross the numbers. That usually works pretty good. But you know, if you can't visualize, if that's kind of a little hard, the way I like to do is draw it out. Like if you have a +1 charge and a -2 charge, how in the world are you going to make them even out? Because there's 2 negative and you're going to probably need 2 of these guys, so they'll balance out to be 0. Okay, so when you draw it out, you'll draw, this is Na positive, and then you'll draw S2 negative, and you're like, hold on a second, that's 2 here, how can I make this one even? So I need to draw another Na positive. So that's +2 and -2, you add up to be 0. So that's how I know I have Na2S right there. That's my formula, okay? A lot of times people just do the crisscross, so that works. That works well too. So another example we want to work on is we want to write down the formula for Al3 plus and O2 negative. So really the question just says formula ionic compound between aluminum and oxygen. So you actually had to figure out these charges on your own. How in the world are we going to figure it out? So if you take a look at the periodic table, aluminum from chapter 2, we talked it was in group 3, so it will always make a +3 charge. You have to go ahead and memorize that, okay? Aluminum is +3 charge. Oxygen is group 6, is 8 electrons to 10 electrons. Well, if it's a neutral atom, because these are actually numbers of protons. And when it's an atom, numbers of protons and neutrons, protons and electrons are the same, okay? So oxygen is 8, neon is 10. Oxygen's like, I need 2 more. So it will take 2 more electrons, and because you receive 2 electrons that are negative charge each, oxygen will turn into oxide ion, which is 2 negative charge. Now, because of that, you have these charges now. Okay, Al3 plus O2 negative. So how do we get it? We can do the crisscross. So now the formula would be Al2O3. Okay, so our answer here is Al2O3. So let's go ahead, now that we know how to write these formulas, we want to go ahead and start learning how to name them. So the tricky part about naming is because we have different kinds of metal ions. So ionic compounds, we have metals in the main table. So let me zoom out a little bit to show you the table. All right, so on our periodic table here, we have the main table and then we have the transition metal area. So these here are the main guys, right? And then these in the middle here are the transition metals. Now, where you have the transition metals, they kind of go a little crazy. They got multiple kinds of possible charges. Some is +1, some is +2, +3, +4. They take all kinds of charges. Okay, so that makes things complicated. So these guys here are called metals ions with variable charges because it changes depending on the situation. Okay, and then there are those on the main table right here that are always fixed. So those metals with constant or not variable charges. Okay, so for example, group 1 will always be +1, group 2 will always be +2. Okay, and then remember aluminum is always +3. So over here it says metal with invariant charge. That's the one we were talking about where the metal ions are fixed charges. So like these guys here. Okay, and that guy. There's one way to name them. And then if it was variable charges, there's another way to name them. They're actually quite similar. So let's talk about how they're similar, okay? In this case here, if your metal ion can change charge, that means you need to write down what charge it is. So you always put the cation name and then whatever charge, and because we want to be fancy, we write it in Roman numerals, okay? Whatever the charge is, you write it in Roman numerals for the charge of this guy, and then you stick it with the name of the anion part. The anion part is whatever IDE or polyatomic ion it is, okay? Now, if the metal ion does not change charges, we don't need to write the Roman numeral. That's the only difference, okay? So cation, Roman numeral, anion with the IDE if you have variable charges. If you don't have variable charges, go straight for the cation metal name and a non-metal IDE ion name. Okay, so let's go ahead and take a look at some examples of metals with that don't change charges. So here's a list here. It says here, metals with variable charges all over the place. Now, invariant charges, group 1, group 2, remember? We talked about that. Group 1 is always +1, group 2 is +2. Aluminum is always 3 plus. Now we got 3 extra here that you can memorize. Silver is +1, zinc is +2, scandium is +3. So I'll show you. Scandium is right here, okay? That's +3. Zinc is right here, that's +2. And then silver is +1, okay? So let me actually give you a better list down here. So what I would do is memorize this list. You don't have to memorize these guys because I mean group 1 and group 2. Just memorize group 1, group 2. Okay? And then who else do you have that's extra? Aluminum is +3, zinc is +2, scandium is +3, silver is +1. Just this few, okay? So group 1, group 2 plus these 4 ions. If you memorize these as the ones that do not change charge, you don't have to write Roman numerals for these. Everybody else, go ahead and write the Roman numerals, okay? So these are older names, cool names, but you don't have to worry about memorizing this as long as you know what charges they are. Okay, what kind of charges they are? Well, it depends on what it's paired with. You know, when they pair together, they'll be neutral and 0 charge. So whatever the negative charge, the anion charges were, it's going to be balanced out by the cation charges. So if you didn't know what charge this was, take a look at the anion side. If the anion was -3, you want to make sure your cation is +3. If the anion was -6, the cation should be adding up to +6. It's just going to be even out the charges basically to make it go to 0. So based on that, whatever charge you calculate for the cation, you write it in Roman numeral, okay? Let's see. Let's take a look at anions here. So anions, you always just take the N out, put IDE when you just change the ions, okay? So we talked about all these guys, right? So this is -1, this is -2, that here is -3 right there. So they gave you some options and you call it IDE. So nitride is N3 negative, oxide is O2 negative, fluoride is F negative, okay? Carbide is not that common, but it's there. All right, so here are some examples here. They have examples of the nonmetal name, the symbol for the anions here and what charges they are and how they got the names. They keep the front of the name, they drop the last part and stick IDE behind it, okay? So go ahead and start remembering how these guys are named if you're not familiar with it yet, because naming will be a big part of your testing as well. You will have to memorize these, okay? Now, here's another list of very, very important ions for you to go ahead and memorize. This is slide number 21, okay? I want you to go ahead and make flashcards and memorize all of these ions here because you will need to use them for naming because chapter 3 has naming involved in it. So let's go over some common ions to kind of, let you be, it's not all strange stuff. Acetate is C2H3O2. Acetate is found in vinegar. It's kind of found in vinegar. Vinegar is acetic acid, and acetic acid actually part of the time exists as an acetate ion in partial modes, okay? And then you have carbonate, CO3. Carbonates, you can find them in like antacids, your Tums, okay? And then you have bicarbonate. That's typically found in your baking soda. Hydroxide, these are found in many things. This is a symbol for basics, anything that's basic basically. So a lot of stuff like, and then you have sodium hydroxide, potassium hydroxide, that actually can be found in like, I guess mostly like liquid plumber stuff too. So, and then you have nitrite. You guys heard of nitrite? Like no nitrates and nitrites in my food. So these are the forms of the ion. So nitrite is NO2 negative, nitrate is NO3 negative. And then you have chromate, dichromate. These aren't as commonly heard of. Phosphates you guys hear about, right? It's in, you find them as sometimes you have too much of it in the water and you don't like it. And then you have hydrogen phosphate, dihydrogen phosphate. So these are all kind of related to each other. And then you have ammonium, okay? Ammonium is found in your glass cleaner typically. Ammonium ion, it's related to ammonia. And then you have peroxide. Peroxide is like in hydrogen peroxide, you have cyanide. You guys hear about that all the time. Cyanide here. And then you got sulfate. And then you got sulfite, and then the hydrogen sulfide and hydrogen sulfate. Or sometimes they call it bi. Same thing here, like hydrogen carbonate, they call it bicarbonate. It's just a different way of naming. So make sure you guys memorize what the formulas and what the charges are, okay? If you notice, sulfite to sulfate, the difference is 1 oxygen. Nitrite to nitrate, the difference is 1 oxygen as well. So, and then when you talk about hydrogen, a bi, you stick an H in front of it and the charge just drops down by 1. So it's not too many to memorize, okay? And then you got perchlorate. So this is a series here. Hypochlorite, chloride, chlorate, perchlorate. You see how every step you go, you add an oxygen. So you can actually have a series. You can also have hyperbromite. Like instead of the Cl, you replace with Br and you name it the same thing, hyperbromite, bromite, bromate, perbromate. Okay, so there's those. So make sure you memorize the sequence here. That will be very, very helpful because polyatomic ions is a huge part in really all chemistry. Okay, so start memorizing this. You will need this for naming and for formulas and for calculations, all kinds of stuff in later chapters. So it's a good thing to go ahead and start memorizing them now. Make flashcards, okay? All right, So if you really wanted to be an overachiever, here's some extra down here that weren't found in up there. But you don't have to go through this. This is just, oh, did you know there's more of them? But if you memorize just these few here, I think you should be good, okay? All right. Here's the list. We were talking about oxyanions, where we're talking about the list here. You see how we were pointing out, you have nitrate and nitrite, and then sulfate and sulfide. It's just like one oxygen short. The one that's a small, less oxygen will be ITE. The one with more oxygen is ATE, okay? And then you have this list here that we were talking about. See how it's hypo, and then chloride, bromide, and then you see how it's ATE, and then per 8, 4. So these all will help you, get things memorized a little quicker because there's a sequence right there. Now, let's take a look at some more examples of polyatomic ions. They have some trends here, but you don't really need to worry too much over here. So these are some more common polyatomic ions, okay? So if you go ahead and just get that list memorized, you should be pretty good. And these are a few here are extra stuff. All right, so why do we need polyatomic ions? Because we needed to name ionic compounds, and you have 2 forms. Remember, we have ionic compounds for the metals that change its charge, that you have to use the Roman numerals, and then you have the metals that don't change the charge, that you don't have to write the Roman numerals. Then you can just piece the pieces together if you remember the anion names. So anions can be simple names with IDE or a polyatomic ion. That's what you have to start memorizing, okay? Oh yeah, going back to that exception. Remember how we said ionic compound is only metal and non-metal? Well, here's a cation that's non-metal. When you have a cation and an anion, like for example, you have NH4 and OH combined together, you call it, it's not technically a metal, right? But it's still an ionic compound because it's ammonium cation and hydroxide anion right there. So in that case, the name will literally be what the polyatomic ions are: ammonium hydroxide. That's it, okay? But most of the time it's going to be metal and non-metal, and just you have to decide, is the metal not changing charge or is the metal changing? So with the metal changing charge and not changing, all you have to do is memorize this list here, which is group 1, group 2, and these 4 here. If it's not on this list here, they're all going to be variable, and go ahead and write down Roman numerals for it. All right, so that was ionic compounds. Now under ionic compounds, sometimes you have stuff that is hydrated, so it has water in it, okay? So what's cool is if you take a look at this guy, this is COCl2.6H2O. So it's not like a, it's a weird dot. It's kind of like a multiply sign, okay? It's a big sign in the middle, almost like the multiplication. So over here is COCl2.6H2O. That's how you write hydrated compounds. That means every time you have a COCl2, there's 6 water molecules in there together with it. And then this one here doesn't have the water. This is called anhydrous. The one with that have no water in it is called an anhydrous compound. This one is a hydrated compound. So what's the name for this guy? Is cobalt is not on a fixed charge, so you have to figure out what charge cobalt is. So chloride over here is 2 negative because each chlorine is a -1 charge. So cobalt will be 2 +2 charge here. So that's why we call it cobalt 2 chloride, and then 6, what's 6? Take a look here, it says hexa and then hydrate. So that's why the name is cobalt 2 chloride hexahydrate. Okay, so you just have to remember how many waters are in there and what each number of water, the prefix name will be. So go ahead and start remembering this too. And then you have, in this case here, if you have CaSO4 half water, half is hemi, okay? So you have hemihydrate there, and calcium is what group? So if you took a look at calcium, calcium is group 2. So calcium is +2 charge. It doesn't vary, it's not variable. So you don't have to write your Roman numeral next to calcium. Just say calcium sulfate. Now, how did you know it was sulfate? Well, you had to memorize that SO4 is 2 negative charge based on the list that we just had. And then chloride is not a polyatomic ion. It's just Cl negative. It's because it's in group 7. It's Cl negative. Okay, so just remember, so we got metals and non-metals, some of them variable charge, some of them not variable charge for the metals. And then you have to know your anion names, which includes polyatomic ions. And then you have to remember your hydrated prefixes. All right, let's try naming some stuff, okay? So this one here, we want to name CaBr2. Ca, again, we looked at calcium, group 2, right? And then we have Br, group 7. That's a halogen, so group 7 right there. So in this case here, CaBr2 is not a variable charge. Br is called bromide, Bromide, and this will be calcium. So the name would be calcium bromide right there, okay? All right, let's go to the next one. We have PbCl4. So you have 4Cl and you know Cl, each one is -1 because it was from group 7. So let's take a look, group 7 right here, -1 charge. So it'll be chloride. And then each one is -1, there's 4, that means your lead. Pb is lead. Pb will have +4 charge. So because Pb is in a transition metal area here, and then you want to go ahead and make sure that you want to go ahead and write down your Pb with the Roman numeral 4 behind it, okay? So let's take a look here. You write Pb is lead for chloride. So you're probably starting to wonder, why in the world is Pb designed for lead, right? You're like, why? Like Pb is all the way down here. Why is it called that? Why is it Pb? And then you start realizing, why is this one called silver? Why is Ag called silver? It's because they have different names previously, and then for some reason we call them something different now. So Pb is actually plumbum, Plumbum, and that's the real name for that. That's why it's Pb. And then you have silver right here, that's Ag. It's actually called argentum, Argentum. That's why it's Ag. You know, like all these names make more sense, right? Gold is Au. That's gold right there. And Au stands for aurum, Aurum. And then what's crazy is over here, like, you know, we call this guy sodium. It's like, how is sodium related to Na? Because the real name for this guy was natrium, Natrium. So, and there is some reason, it's just that somehow along the way, names got changed, and then they never changed the symbol. So now you just have to remember sodium is Na, and really the old name was natrium. Okay, so just want to clarify a little bit. So this guy over here in our periodic table, this one's lead, okay? Lead for chloride. All right, let's do more naming. So now we want to talk about naming for a polyatomic ion. Well, this one we're gonna let you guys kind of cheat a little bit because you don't have it memorized yet, right? So let's take a look. So it says Cr2O7, okay, and Li2Cr2O7. So now you gotta look for the name for Cr2O7. You have to recognize that that was a polyatomic ion. So let's flip back, take a look at our charts, try to find Cr2O7. Right here. See here, Cr2O7 is 2 negative. What is it called? It's called dichromate. Okay, so we know that dichromate is 2 negative charge. Let's go back to the question. Right here. So Li2Cr2O7, Li is group 1 right here, so it doesn't change. I don't need a Roman numeral, so it's simply lithium dichromate, okay? right there. So you do have to memorize your polyatomic ions. If you don't, you get into, I guess, a big pickle. All right, so that was ionic compounds. So let's take a look at molecular compounds now. For molecular compounds, it's still, you still gotta know the parts, but there's gonna be, everybody's gonna be non-metal. There's no metal and non-metal here. It's everybody's non-metal. So when you have both of them non-metal, you need to have prefix, name, okay? The first element, just stick an element name. The second one, put IDE behind it, okay? So what are the prefixes is pretty much the same stuff as the one you just memorized for the hydrate. So that will make it pretty easy, right? So when you have mono though, if you have one thing for the first element, you don't have to write mono on it, okay? So let's go ahead and practice. It's easier to practice with examples. And you'll have plenty of examples when you do dynamic study modules, when you do your homework, take your quizzes on Pearson, mastering, all kinds of problems to test out, okay? And if you guys ever need an extra, let me know, I got more. Okay, Ni3. So you have to figure out N is nitrogen, I is from iodine, but remember the back one, you always have to make sure you stick an IDE, so it'll be iodide. Okay, how many iodides are there? It's 3 of them. So it'll be nitrogen. We don't need the mono because it's 1. So it's nitrogen triiodide. Okay? So that's how you name the first one. Right here. All right, the next one is PCl5. P is phosphorus. So I guess I'll show you on a periodic table. Phosphorus is right here in group 5. We just did iodide, which is group 7 right here, and nitrogen up here. Now we're doing P and Cl, okay? So both are non-metals, right? So it's phosphorus, only one, you don't need a mono. So phosphorus, how many chlorides? There's 5, so it's penta. So it's phosphorus pentachloride, okay? Right there. Now, the next one you have P4 and S10. So P would be phosphorus, again, 4 is tetra, 10 is deca. Okay, so you just, those are your prefixes. So this would be tetraphosphorus deca sulfide, IDE, right there, okay? So you just have to remember. So a lot of times when you're naming stuff, people mix up the rules for ionic and for molecular compounds. So always take a look at the compound and say, is this a molecular compound or is this an ionic compound? Because ionic compounds have a different naming system than a molecular compound. So try to identify which one it is first, and then go to the mode of how do I name this type of compound, okay? All right, so after we name ionic and molecular compounds, we want to continue under molecular compounds and start naming acids. Because, you know, acids are a big part of our chemistry. We have a lot of acids in labs that we'll see. Some characteristics of acid is always going to have an H plus in there. Taste sour, the ones that you can taste. I will never, never, never want anyone to taste any acids in the lab. Never, ever, ever do that. But you can taste acids that you can find around the house, like vinegar. Vinegar is a type of acid and it tastes sour, okay? Acid will dissolve many metals. You'll see these in some experiments, especially for the first experiment for Chem 1. You have like chemical reactions that you put metals in, and some of the metals will like just disappear, and some of them just sit in there and do nothing. But acids will dissolve a lot of these metals, okay? And then formula will start with an H, HCl, that's acid, that's H2SO4, that's another acid. So when you do your experiments and you put the piece of metal into your acid and it starts bubbling like this, you'll see that it starts to disappear. So it actually tells you zinc metal will be dissolved by hydrochloric acid. It's kind of cool. You'll see this experiment in lab. And another cool one, cooler than zinc, is magnesium. The second you put magnesium in, it like pretty much almost disappears. It's such a quick and fast reaction, and the test tube will get really warm. So it's an exciting one to watch. All right, so we gotta know how to name the acids. Okay, now that we know some things about acids, how do we name them? Well, there's two kinds of acids. We have binary acids and oxyacids, kind of like the ones, polyatomic ion with the oxygen. We call them oxyacids because it has the polyatomic ion in there. So binary acids are the plain one, like H and something without oxygen. Okay, in this case, if you have binary acid, you have two elements, you call it hydro, whatever name, ic acid. So chlorine will be hydrochloric acid. If you have iodine right here, it will be hydroiodic acid. If you have bromine here, it will be hydrobromic acid. Okay? And then you have oxyacids here. Now remember, if your polyatomic ions end in 8, it will be ic acid. If it ends in ite, it'll be us acid. Okay? So let's, that means you need to remember this list. You see, I bring this back up again. Make sure you memorize this list. If you don't know this list, it'll be very hard to name everything. And naming is a big part. So you want to make sure you know how to name that stuff. Okay? So let's take a look at some examples. Okay, don't look at the answers yet. Let me cover it up. What's the name of this guy? HI. So another trick to naming acid is make sure your compound has AQ behind it. AQ means aqueous, means it's dissolved in water. The only way something can become an acid is if it's dissolved in water. Okay? So HI aqueous will be a binary acid because it's H and something that doesn't have oxygen. So it's hydroiodic acid. Okay? Right there. Okay, so let's do another one. This one here is an oxyacid and it has a polyatomic ion. Then you have to remember, why in the world is the name of this ion? So C2H3O2 is a -1 charged ion called acetate. And acetate is what you can find in vinegar. So really this formula is for vinegar. Okay, the white vinegar that you see at home is diluted in a certain amount into water. Well, that's the formula for it. So this would be an oxyacid. So we just need to know this, guys. This is acetate. So take the ATE, turn it into ic acid. So it'll be acetic acid. So we call it acetic acid. Okay? So you just have to memorize your polyatomic ions, basically. If you don't, it's going to be difficult to name a lot of stuff. Let's practice some more. Let's do this one. So you notice here how these guys here, well, chlorus, OS has to come from something with ITE. Okay, so then you have to look at what chloride ion looks like. So you have to memorize what chloride is. So chloride comes from a list where you have hypochlorite, chloride, chlorate, and perchlorate. So chloride is the second one with 2 oxygens. So this is what it would look like. Chlorite. Okay, and then you put H with it, so your formula will be HClO2. All right, phosphoric acid comes from phosphate, ic and ate. So then you have to remember what phosphate look like. Phosphate actually is PO4, 3 negative charge. So you would need 3 hydrogens to pair with that. I'm gonna do a crisscross, remember? So H3PO4 is the formula for phosphoric acid. Remember, to be official, you have to put an AQ behind these guys, okay? Now, hydrobromic acid is a binary acid, so you just take the BR here, so it would be HBr, okay? So we want to practice naming these guys. All the answers are on there. Oh, it's on the back, so I don't have to. So this one here is a binary acid, right? And so binary acid, this one is S, so is hydroic acid, sulfuric acid. So hydrosulfuric acid, okay? And then this one here is ClO3, That's a polyatomic ion here. This ion name is chlorate. Okay, so it'll be chloric acid. This ion here is acetate. So this will be acetic acid. Okay, so you do have to memorize the name. So let me go ahead and show you the answers spelled out really nicely on your slide. This is slide number 39. Okay. All right. So that's the answers right there, and you see how we got them. And it's very, very important that you start memorizing your polyatomic ion. So overall, this is a summary of naming. So you have ionic, and then you have molecular, and the molecular you have acids. Ionic, if you have metal and non-metal here, molecular is only non-metals in general. And then if you have metals that don't change the charge, you just go the cation without Roman numeral, IDE. If the cation changes its charge, you have to put the Roman numeral in. And then molecular is prefix, except for mono, and then the name of the first one, prefix for the second, and then IDE. And then you have acid, we have binary acids with two things, oxyacid has an oxygen and polyatomic ion. So the base of ATE turns to ic acid, ITE turns to us acid, and this is hydro something ic acid. All right, so that's the first part of chapter 3. We're going to take a break for now. This is part 1 of chapter 3. When we come back, we're going to do the second half of chapter 3.